Good morning. Good morning. Right. What is the last subtopic? I sent you a note yesterday in the WhatsApp group. Did you go through it? Huh? You saw that I have sent. You saw that you thought that I had just sent it for fun, no? Because I was jobless at home. I decided to send you a note, and you just ignored, no? Right. Yeah, it is O levels, but there are some people here who haven't done the Excel O levels, no? So that is why I sent it. Because to what I know, you haven't done that for Cambridge O levels or local O levels. So that is why I sent you that note. I expected you to go through it. Okay, fine. People online, hello, hi, can you hear me? Good morning, are you there? Hello. Hi. Hello. Good morning, good morning. Right. Then, in the theory cube, up to which point did we discuss? We spoke about that the big distance units about astronomical units. Are there any questions for homework? Are there any questions? What? Starting from 16th. Huh? Page 60, you mean? Question 34, page. Right. There's a question 34 on page number 60. Procyon is the brightest star. In the Canis Minor, the graph shows how the radiated intensity from it with wavelengths, how the radiated intensity varies with the wavelengths. A website states that Procyon has twice the diameter as the sun. Assess the accuracy of this statement. Luminosity of Procyon is given, the diameter of sun is given. So all you need to do is find its diameter and show that, and check that if it is twice the diameter of the sun or not. Okay. So what is the equation which connects the intensity and wave intensity and the diameter, intensity and the radius? L equals force. Yeah. Luminous. No. Wait. Luminosity. Tell me what is the equation for luminosity? That is 4 pi r square. Sigma t to the power 4. Am I right? Right. And then guys, this wavelengths and this maximum intensity, there is an equation connecting it. What is that? Lambda max. Lambda max into t equals lambda max into t equals 2.89 into 24 minus 2. What law is this? Wien's law. So lambda max is, how much is this? It's about, it's slightly more than 450, no? 450 is here, no? This is 450, but the peak is a bit to the right of that. What if we take it as around 400 and 460 460. So 460 into 10 to the power minus 9, it's in nanometers, into T is equal to 2.89 into 10 to the power minus 3. So this will give you the temperature of that star. 2.89 into 10 to the power minus 3 divided by 416 to 10 to the power minus 9. 6,282.6 Kelvin. Correct? These are temperature of that star. And then the luminosity of that star is given 2.65 into 10 to the power 27. And we want to find the radius. So I'll use this equation. Luminosity is 2.65 into 10 to the power 27. 4 pi r square. What is the sigma? 5.67 into minus 3. Correct? Into t to the power 4, where the t is 6,282.6. And that to the power 4. So from this equation, I need to find this r square and then get the r. That will give you the radius of this star. See. R square is 2.38 into 10 to the power 18. Square root of that will be 1.545 into 10 to the power 9 meters. So they are saying, the website states the Procyon has twice the diameter. Now I'll check the diameter of this, which will be radius into 2. That is 3.09 into 10 to the power 9 meters. Where the diameter of the sun is 6.96 into 10 to the power 8 meters. So the diameter of the sun, so 3.09 into 10 to the power 9, that divided by the diameter of the sun, which is 6.96 into 10 to the power 8, will tell you how many times it is. Isn't it like 4 times? Huh? I'm getting 4.43 times. Yeah, slight difference can be there, but it should be somewhere around 4 times. Where the website has stated Procyon has twice the diameter of the sun. But we are getting it's 4 times the diameter of the sun. So the statement is wrong. Have you got this 4 times? So then write the final statement. No, the statement is incorrect. What was your final answer? Did you multiply? You have taken the radius. Right. What's next? What's the next one? Page number? Right, page 76, question 42. Looks like a small one. Sirius is the brightest star in the night sky. The intensity of Sirius is measured to be 1.09 into 10⁻⁷ watts per square meter. Calculate the distance of Sirius from the Earth. Luminosity of Sirius is given 8.94 × 10⁻27. Right, there's intensity is equal to luminosity over 4 pi r square. Correct? Intensity is equal to luminosity over 4 pi r square. So intensity of Sirius on the Earth is 1.09 into 10⁻⁷. That is equal to the luminosity of the star is 8.94 into 10⁻27. That divided by 4 pi into r square, where r is the distance from Sirius to Earth. Correct? So cross multiply to get the r square subjected and get the r subjected. Eight 8.08 into 10⁻16. Now, after being squared, this is the distance. 8.1 into 10⁻16 meters. Okay, what's next? Page number 49. Page number 49 or question number 4? Page 49. Page 49, question 28, is it? You've done it. Page 86. Question 49. The mean intensity of the solar radiation arriving at the Earth is given 1.37 kilowatt per square meter. The distance of the Earth from the Sun is given. Show that the luminosity of the Sun is about this much. So intensity is equal to P over 4 pi r square. So the intensity is at the Earth coming from the solar radiation is 1370. It's 1.37 kilowatt per square meter. So 1370. P is what I want, the luminosity over 4 pi. R is 1.5 into 10⁻11 square. From here you can get the P subject. .87. Yeah. Watts. The energy radiated from the Sun results in a decrease in the mass of the Sun. Calculate the decrease in the mass of the Sun due to this radiation over a period of 1 year. 1 year is given this much of seconds. the energy radiated from the sun, decrease in the mass of the sun. Calculate the decrease in the mass of the sun due to this radiation over a period of 1 year. Right. Guys, using energy equals power into time, I can find how much is the energy radiated in 1 year, which is power is 3.87 into 10 to the power 26 into the time is 3.15 into 10 to the power 7. This much of joules is radiated from the sun. Okay. Which is 1.219 into 10 to the power 34 joules. This much of energy is radiated from the sun for a year. Then to see what is the mass corresponding to that, I can use E equals mc square to see how much the mass which is decreasing. So the energy is 1.219 into 10 to the power 34. Mass into C is 3 into 10 to the power 8, and that needs to be squared. Which is 1.35 into 10 to the power 17 kilograms. Mass of the sun is reducing by this much every year. Okay. What's next? That's all. Page 98, question 56. The image below of a healthy man was taken with an infrared camera. Darker areas on the image represent areas of high temperature. From this image, it was estimated that the average skin temperature of the man was 307 Kelvin. Calculate the peak emission wavelength of the thermal radiation emitted by the man. Treat the man as a black body radiator. So lambda max into T is equal to 2.89 into 10 to the power minus 3. Okay. What do you call this constant? Green's constant. So lambda max will be equal to 2.89 into 10 to the power minus 3 divided by 307. (9.41) into 10 to the power minus 6 meters. Right. Part B. Calculate the rate at which thermal energy is radiated from the man. Treat the man as a black body radiator. Surface area of the man is given 1.2 into 10 to the power 1.2 square meters. So L equals sigma A T to the power 4. What is sigma? 5.6. 5.67 into 10 to the power minus 8. Area is 1.2. Temperature is 307 to the power 4. That is 604 watts. In practice, the net rate of energy lost by thermal radiation is different from that given by the calculation in part B. One reason is that the man is not a perfect black body radiator. Suggest two other reasons. Yeah, the temperature that we have found is 307 Kelvin is the average temperature. No? So different parts of the body can be at different temperatures. So that means the rate from different parts of the body will not be the same. That is one. Another one. No, it depends on the area and the temperature. No, what do you mean by depends on the person? The temperature depends on the person. So it depends on the temperature.
Yeah, so then some people have higher average.
Yeah, so we are talking about this person who is at that temperature now.
No, so they are not using this person as a generalized example.
The question is in practice, the net rate of energy lost by thermal radiation is different from that given by the calculation B. One reason is that man is not a perfect black hole. So they are talking about this man, right? Calculated value for this man is in practice. So write the first one. And the entire body is not at the same temperature. The entire body is not at the same temperature. So different parts.
So can you repeat the answer?
The entire body is not at the same temperature. Yeah, that's enough actually. So 2 mark. No? So 1 point is the entire body is not at the same temperature. The other point, the area that we calculated as 1.2 square meters, how reliable it is. How do you measure the surface area of a person? Do you think there's any method, any reliable method to measure the surface area of a person? Does a man look like a cylinder? What? A cuboid? Like what? How do you find the surface area of a man? Can you think of a method that you? Huh? You can't.
No, you use integration for the curved parts, and for the straight part, you use just the triangles or whatever.
It's constant because it changes here.
Yeah, it depends on his position. Like if I stand with my hands, with my body, then the surface area is different. If I raise my hand, the surface area exposed to the environment is different. But anyway, that is not my point. My point is what they have calculated here, what they have given here is 1.2 square meters. Is definitely not an accurate value. Can be close enough, but not that accurate value. So you can mention about that. The surface area of the man cannot be measured precisely or accurately. Yeah. True. While doing the experiment, the temperature can change. Yeah. But don't mention both points about the temperature. One about temperature and the other one Right, what's next? That's all. Right, guys, then right, guys, from the theory to page number 7. You don't have it. You don't have it. Coding it is no. Anyone else? Yep. Right. Trigonometric parallax. To measure the distance to relatively close stars. Okay. To measure the distance to relatively close stars, astronomers use a method which is commonly used in surveying, known as trigonometric parallax. As the Earth moves around the Sun, a relatively close star will appear to move across the background of the more distant stars. This optical illusion is used to determine the distance of the star. The star itself does not move significantly during the course of the observation. To determine the trigonometric parallax, you measure the angle to a star and observe how that changes as the position of the Earth changes. We know that in 6 months, the Earth will be exactly in the opposite side of its orbit, and therefore will be 2 astronomical units from its location today. Using observations as a star which is to be measured against a background of much more distant stars, we can measure the angle between the star and the Earth in these 2 different positions in space 6 months apart. Okay. So based on that, you can find the distance to the star. So this shows you how it is done. So guys, let's say that we want to find the distance from the Earth to a star somewhere here. Okay. Then here is a background star, and this is the star to which we are going to measure the distance. So if you look, if the Earth is here today, the Earth takes 12 months to go around the Sun, which is 1 year, 365 days. So exactly 6 months later, the Earth will be on the exact opposite side of the diameter. Okay. So if you can draw two lines at the two different position of the Earth to the star. And if you take this angle to be 2 theta, you know this distance, the radius of the orbit of the Earth around the Sun, you know, r. If you take this angle to be 2 theta, you can come up with a triangle here. This is theta, half of 2 theta. So this is r, this is d. By simply using tan theta equals r over d, you can find the distance. Can you please go through it? Is that it? Okay. By tan theta equals r over d, you can find the d. And guys, this theta is going to be
So, but we
an
need to know
extremely
the
small
theta.
value. This theta will be a small angle. Okay, it won't make a big, it is not a big angle, so it will be a small one. So actually, when the theta is really small, tan theta value will be equal to the theta value. So for an example, put your calendar in the radian mode and tell me, check and tell me what is tan 0.1. What is tan 0.1? 0.1. Tell me what is tan 0.05? 0.05. Tell me then what is tan 0.12? 10 0.13. 10 0.15. 10 0.2. 10 0.3. 10 0.4. 10 0.5. Check. I'm asking you to check for a reason. 0.55. 10 0.6. 0.6. Can you see that when the theta is getting bigger and bigger, then the tan value is getting deviated from the theta value? When it was tan 0.1, it was almost 0.1. So when you keep on slowly increasing the theta value, the tan value gradually moves away from that theta value. So when you check tan 0.6, now it has gone to 0.68. Check for tan 0.7. 0.84. Tan 0.8. 1.0. Now it's moving away and away. So my point is, when the theta is really small, and also the theta is in the radian mode, tan theta value will be equal to the theta value. So anyway, the theta that is involved in these cases in measuring the distance, the angle it makes the star and the sun and the earth, that is going to be an extremely small value, an angle in the range of 0.1, 0.2 radians. So tan theta will be almost the same as a theta. That is what they have given there in the note. At small angles, as we are usually using astronomy, tan theta is approximately equal to theta. So then if you replace the tan theta with theta, straight away d will be equal to r over theta. Exactly. Yes. Right. Then the next one, the next page. Standard candles. Standard candles. We saw previously that the brightness of a star was linked to its size and its temperature. Okay. Brightness of a star was linked to its size and its temperature. However, Stefan Boltzmann law only considers the power output of the star at its surface. The luminosity of a star is its overall power output over its entire surface. How bright it looks to us, energy we receive from it, how far away the star is. It follows that if we knew the power output of a star, then how bright it appears to us on Earth would give away its distance. Okay. Right. Guys, here it says the intensity is equal to a log 4 pi d square. That is, we already know that if the intensity is at a point from the source with luminosity L at a distance d, the intensity is given by LO I equals LO 4 pi d square. That is okay. Okay, that you know, that is what told in this part. Some stars, including some variable stars, the next page. Okay. Some stars, including some variable stars and supernova, have properties which mean their luminosity can be determined quite separately from other measurements. These are known as standard candles. If we have a figure for the luminosity and measure the energy intensity of the star reaching the Earth, we can then calculate how far away it is by comparing it with a standard candle with same luminosity. Read that part again. Okay. We already did a question on this today. So if you know some stars, including some variable stars, have properties which mean their luminosity can be determined quite separately from other measurements. These are known as standard candles. If we have a figure for the luminosity and measure the energy intensity of the star reaching the Earth, we can calculate how far away it by comparing it with the standard candle with the same luminosity. So if you know, now there's a worked example here, the luminosity of Betelgeuse is 5.4 into 10 to the power 30 watts. It is radiant energy intensity at the Earth is 1.1 into 10 to the power minus 8 watts per square meter. That means when it reaches Earth, per square meter, the energy reaching is 1.1 into 10 to the power minus 8 watts. That is the power reaching the Earth per square meter. So how far is Betelgeuse? So how it works here is, now let's say this is the Earth. Betelgeuse is here. So the energy radiated from Betelgeuse is in all directions. Okay. So if the distance from Betelgeuse to Earth is d, and if the luminosity of Betelgeuse is L, its intensity when it reaches Earth here is given by LO 4 pi d square. So the luminosity, you know, 5.4 into 10 to the power 3. You know the intensity 1.1 into 10 to the power minus 8. So using this equation, you can find the distance from Betelgeuse to Earth. Okay, we did already a calculation on that. That is what given here. Take the tute again. Question tute. Turn to page number 51, question 29. Can I do that? Page 51, question 29.
So I don't understand why do they call it standard candles and what is standard candle?
Right, question 29. A standard candle in the galaxy M81 has a luminosity of 14,800 times the luminosity of the sun. The intensity of radiation received from the standard candle measured at the top of the Earth's atmosphere is given. By the time it comes to the Earth, this is the intensity. Calculate the distance of the M81 galaxy from the Earth. So we can use intensity is equal to the luminosity over 4 pi d square or 4 pi r square or whatever, where the distance is what we refer here by d or r. So the intensity is 3.64 into 10 to the power minus 17. The luminosity of the candle is given 14,800 times luminosity of the sun, which is 3.83 into 10 to the power 26. That over 4 pi d square, where d is what we need to find. Is it 1.1, 1.11 into 10 to the power 23? Yes? Are you getting that answer? Yes. Right, guys, page 55, question 32. Wolves 359 is a red dwarf star. The distance of the star from the Earth was first determined from parallax measurements made by the astronomer Max Wolf. The parallax angle was 2.01 into 10 to the power minus 6 radians, an extremely small angle. Calculate the distance in meters, make sure the calculate is in the radian mode. No, doesn't matter if you are just using theta, but if you are using tan theta, it has to be in the radian mode. Calculate the distance in meters of Wolf 359 from the Earth. The mean distance from Earth to Sun is given 1.5 into 10 to the power 11 meters. So guys, if we put up a triangle here, Sun here, the Wolf 359, I will label it W, and the Earth is here. The parallax angle they have taken 2.01 into 10 to the power minus 6. This is the angle. Theta. Okay. So the mean distance from the Earth to the Sun, we know this one, 1.5 into 10 to the power 11 meters. But now they are telling you to find the distance in meters, the Wolf from the Earth. So this distance is what needed. I'll take this as D. Okay. So you can stick to basic trigonometry. Sine theta equals opposite over hypotenuse. Sine theta equals 1.5 into 10 to the power 11 divided by D. Opposite over hypotenuse. So D equals 1.5 into 10 to the power 11 over sine theta. Sine 2.01 into 10 to the power minus 6. The cal should be in the radian mode.
So you said if the value is small, we can use theta instead of sine theta.
Yeah, can do actually. Are you getting 7.46 into 10 to the power 16? Yes.
So light years is speed of light into years, right?
365 into 24 into 3600. Okay.
So the name is a bit confused. The name should be like
1 light year, the distance traveled by the light in 1 year. How else you want it to be?
they should specify because there's no guarantee that you will figure it out.
Where have they used it? Where have they used it? They haven't used it in this question.
No, I just
Ah.
asked.
Right, part 2. Explain why the parallax measurements can only be used. This method can only be used to determine the distances to a relatively small number of stars. Yeah, you can use this method only to stars that are close by. Why? You need some reference stars at the background. If you don't have those reference stars at the background, you can't find that distance. You locate the star based on the stars that are at the background. So if it can only be used for the stars which are close by. So write the answer. This method only can be used This method only can be used to measure the distance of close stars. To measure the distance of close stars with reference to the background stars at a distance.
So could you repeat the last part?
Sorry?
You tell the answer.
Yeah, this method only can be used to measure the distance to close stars. With reference to the background stars at a distance. Okay. Can you quickly get the answer for the next part, part B?
Can you show the before question, the 30 to 30 second?
Huh?
Which thank you.
Right, the graph shows how the intensity of radiation from the star varies with wavelengths. Show that the surface temperature is about 2700 Kelvin. There's what is the lambda max? 1 point, 1 point, no,
So 1.1.
it's 1 point, no, it's 1.075. Here, right? You can see the horizontal scale.
So when I use that value, I get something close to the 700.
Let me check. So the lambda max is 1.075 into 10 to the power minus 6 meters. It's micrometers. So lambda max into T is equal to the Wien's constant, which is 2.89 into 10 to the power minus 3. So T will be equal to 2.89 into 10 to the power minus 3 divided by 1.075 into 10 to the power minus 6. That is 2688 Kelvin. What did you get? 2688 Kelvin we are getting. Didn't you convert micrometers to meters? 2688 Kelvin, correct? Close enough to 2700. Okay.
So if it is 2600 also would it be?
What is the lambda max you have used? Tell me that.
Right. If that
Not really, not really. Part 2, the radius of the sun. The radius of the wolf. Radius of the sun is r sun. The radius of the wolf is given 0.16 times r sun. It is claimed that the luminosity of wolf 359 is less than 0.1% of the luminosity of the sun. Did you see this claim is correct? Radius of sun is given, L sun is given, luminosity of sun is given, temperature T is given, 2700 Kelvin. So we need to check the luminosity of wolf. No. Luminosity is equal to 4 pi r square into sigma T to the power 4. Correct? So which is 4 pi. The radius of wolf is 0.16 times the radius of the sun, which is 6.96 into 10 to the power 8. That square into sigma is 5.67 into 10 to the power minus 8. T is 2700 to the power 4. This gives you the luminosity of wolf. which is 4.6957. Or 6958 into 10 to the power 23 watts. This is the luminosity of wolf. So check whether it is less than 0.1% of the luminosity of sun. So I'll take this luminosity of the wolf over luminosity of sun into 100 to see what percentage of sun is the luminosity of the wolf. So that is going to be luminosity of sun is 3.83 into 10 to the power 26 multiplied by 100 is 0.122 or 0.123. So luminosity of wolf is 0.12%, 123% of luminosity of sun, which is more than 0.1%. Do you whether the claim is correct? No, the claim is incorrect. Claim is incorrect. Yes.
So do you have to show that percentage?
Yeah, no. You have to make a conclusion. They are telling that the intensity of wolf is less than 0.1% of the luminosity of sun. So I calculated what percentage of sun's intensity is the intensity of wolf, which is more than 0.1%. You need to. There will be 1 mark allocated for that. And then
The claim is incorrect.
claim is incorrect. There's page 65, question 37. Page 65, question 37. Can you? Page 65, question 37. Okay, right. The astronomer Hertzsprung used parallax to determine the distances to some of the variable stars known as Cepheus. Using parallax measurements, astronomers can determine distances to all stars with a parallax angle larger than 2.4 into 10 to the power minus 7 radians. The parallax angle has to be more than this. The variable star Alpha Cephei is 4.6 into 10 to the power 7 meters from the Earth. Deduce whether the distance to Alpha Cephei could be determined from parallax measurements. Distance from Earth to Sun is given. So the Sun is here, Earth is here, and the star is here. Okay? Is a star. So this angle, parallax angle, we'll take it as theta. Calculate it and see whether it is more than 2.4 into 10 to the power minus 7 radians or not. So this distance, the distance from the Sun to the Earth is 1.5 into 10 to the power 11. From Earth to the star is 4.6 into 10 to the power 17. So taking sine theta opposite over hypotenuse. 1.5 into 10 to the power 11 divided by 4.6 into 10 to the power 7 sine theta, opposite over hyperbole. Sorry, 17. That gives you 3.26. into 10 to the power minus 7 radians, isn't it? So that is more than 2.4 into 10 to the power minus 7 radians. So the conclusion is yes. You can use this method. Correct? It can be determined using parallax measurements. It has to be more than 2.4 into 10 to the power minus 7. Done. Cepheids are a type of standard candle. Describe how standard candles can be used to determine the distance to stars. That's a big number. Right? 60. Are a type of standard candle. Describe how standard candles can be used to determine the distances to stars. So standard candle means you know its luminosity. So if you know its luminosity, if you can measure the intensity. Now let's say there is this star, you know the luminosity. And there is another star here. And if you can measure its intensity here, using intensity equals L over 4 pi d square, you know the intensity, you know the L, you can measure the D. Okay, so write the answer. It's a 3 marker. The luminosity of a standard candle is known. Luminosity of a standard candle is known. Full stop. So by measuring the intensity,
The luminosity of standard candle is
known, it's a known value. Full stop. But that's not that. By measuring the intensity, and using the equation I equals L over 4 pi d square, the distance can be found, or distance can be determined. Okay,
So by using the equation,
by using the equation I equals L over 4 pi d square, what I have given here, the distance can be determined. Okay,
which
part C we have done, but the C part 3 we'll keep it for later. Page 80, question 45. Page 80, question 45. the sun is a main sequence star. State what is meant by a main sequence star. What is a main sequence star? Huh? Okay, it's in the. How is it stable? Forces are balanced. Very good. So the outward force due to nuclear fusion and the inward force due to gravitational forces are balanced. So it is at a stable period. So right. The outward force due to nuclear fusion the outward force due to nuclear fusion is equal to or is balanced by gravitational forces. So the star is stable. So the star is stable. Quickly get the answer to the part B. Right. The sun will eventually leave the main sequence and become a red giant star. The luminosity of the sun is given. Show that the current radius of the sun is about this much. Surface temperature of the sun is given. What is the equation to use? L equals 4 pi r square sigma t to the power 4. So the current luminosity is 3.83 10 to the power 26. To see the radius, 4 pi r square. Sigma is how much? 5.67 into 10 to the power minus 8. Temperature is 5780 to the power 4. From here we can find the R. I'm getting 6.94 into 10 to the power 8 meters. That is the distance, that is the current radius of the sun. Correct? as a red giant star, the radius of the sun will be about 150 times its current radius. Its luminosity will become 1600 times its current luminosity. Lambda max is the wavelength at which peak power radiation occurs. Show that when the sun is in its red giant state, lambda max is about this much, the current radius of the sun is given. Right. So when it goes to the red giant state, we can find the temperature by using L equals 4 pi r square into sigma T to the power 4. So when it goes to the red giant state, its luminosity is 1600 times its current luminosity. So it will be 1600 times the current luminosity is 3.83 to the power 26 equals 4 pi into r square. R will be 150 times the current radius. So it will be 150 times 7 into 10 to the power 8. That square. So 4 pi r square. Sigma T to the power 4. Sigma is 5.67 into 10 to the power minus 8. T to the power 4. So this will tell you what will be the new temperature of sun. Hold on. So T to the power 4, you get it. And then to get the T, you have to take the to the power, that value to the power 104, which is 2972 Kelvin. Correct? This will be the temperature once it reaches the red giant stage. So, but we are told to find the lambda max. So, lambda max into T is equal to, what are the constant? Means constant? 2.89, 8 into 10 to the power minus 3. So, this gives you the lambda max. Is it 9.75 into 10 to the power minus 7 meters? Which is, if you take it to one significant figure, 1 into 10 to the power minus 6 meters. Correct, right? 9.75 into 10 to the power minus 7 means one significant figure, 10 into 10 to the power minus 7, which is 1 into 10 to the power minus 6. Is that okay? Any questions, anyone? People online? Hello?
So how does it
Hi.
become 1 into 10 to the power minus 6?
Did you get 9.75 into 10 to the power minus 7?
Yeah.
Okay, you can leave that as your answer. They're telling to show it is about 1 into 10 to the power minus 6. Now, what I told is, if you take this value to one significant figure, it is this.
Understand, yeah.
9.75 into 10 to the power minus 7 means 10 into 10 to the power minus 7. That is 1 into 10 to the power minus 6. Shweta, are you new to this class? It's there in your mail. Please check your mail. All right, guys.
Sir,
Yeah.
someone wants to repeat the answer for 45A, sir. What is meant by main sequence star?
What is meant by a main sequence star is Now, yesterday in the WhatsApp group, I have sent a note. No, please read it. It tells you what is a main sequence star. Anyway, I'll tell you now. Listen. In the sun, that note guys tells you exactly how a star is born, what is the birth of a star, and what are the stages of the star, what and what happens. Okay. So now, if you take the sun, it's about 4.5 billion years old. So how it formed, what happened after that, what are the stages, what happens within it, what is nuclear, how does outward forces come due to nuclear fusion, and there is this inward forces due to gravitational forces. If the gravitational forces are bigger than the outward nuclear fusion forces due to nuclear fusion, then obviously it becomes smaller in size. Correct? No? If the nuclear fusion outward force is bigger than the attractive gravitational force, then it will become bigger in size. Correct? If you take a ball, if the outward force is bigger than the inward force, it will become bigger. If the inward force is bigger than the outward force, it will become smaller. It becomes denser. Correct? So what is meant by this main sequence star is the outward force and inward forces are balanced. So it is in a nice stable period. Stable state. Understand? So what is meant by a main sequence star? A star in which the outward forces are balanced by the inward forces. So you have to mention the outward forces due to nuclear fusion and inward forces due to gravitational forces. So those two are balanced. Okay, right. Then part 3. At this stage of its evolution, the sun will be classified as a red giant star. At this stage of its evolution, the sun will be classified as a red giant star. The wavelength of red light is between 6.2 into 10 to the power minus 7 to 7.8 into 10 to the power minus 7 meters. The wavelength of red light. Comment on the value for lambda max and this classification of the sun. So guys, the lambda max that we got is 9.75 into 10 to the power minus 7. Lambda max that we got is 9.75 into 10 to the power minus 7. Listen to this carefully. Lambda max that we got is 9.75 into 10 to the power minus 7. And the wavelength of red light is 6.2 to 10 to the power minus 7 to 7.8 into 10 to the power minus 7. Okay. So the lambda max that we have got is more than the range what they have given for the red light. So that means this wavelength doesn't correspond to a red light. More than that. Okay. Which is in the range of infrared, not red light. Then the question is, why then it is called a red giant star? If it is not anything, if that wavelength is not red light, why do you call it red giant star? You call it red giant star, that star will look red in color. So if this wavelength is not the wavelength of red, how will it look red? Yeah. Now tell me guys. So what is this wavelength? What is this wavelength?
So is it because?
It is a
Is it because it's not in the main sequence at this point, but when it's in the main sequence, it's written?
no. Red giant is after it passes the main sequence when it is moving towards the middle of its towards after the main sequence. It goes to this stage where it's called as a red giant star. So the question is, comment on the value of lambda and why it's classified and this classification of the sun, why it is called a red giant. Now this wavelength is 9.75 into 10 to the power minus 7. Is it the only wavelength which is emitted? And you remember the graph, it's a graph like this, no? So what you have here is this wavelength. It's not the only wavelength which is emitted. So there will be wavelength which is emitted with a wavelength less than that and more than that. So obviously the only visible color that will be emitted which is less than lambda 9.75 into 10 to the power minus 7 will be the red light. There will be which is red light which is also emitted. So what we have calculated here as lambda max is only one wavelength where the peak is there. But there is light which is emitted with a lesser wavelength as well, which will be falling in the band of red light 6.2 to 7.8. So it will be looking as a red giant ball. So that is why you call it a red giant star. Right answer.
So
The value of light.
refraction is not an explanation because due to energy loss, the wavelength should increase, right? So
No. When as it is coming in, you can expect the wavelengths to be reducing. That can also be given as an answer. Yes. When the speed is reducing from vacuum to air, the speed is reducing. So that means the wavelength will be reducing. That can also be given. Yes. Right. The lambda max calculated. Lambda max calculated is the wavelength lambda max calculated is the wavelength at which the luminosity is maximum. Full stop. There will be wavelengths emitted by the sun. There will be wavelengths emitted by the sun. There will be wavelengths emitted by the sun, which is in the range of red light. Which is in the range of red light. Full stop. Also when the light enters the atmosphere of Earth. Also when the light enters the atmosphere of Earth, wavelength will decrease due to diffraction. Due to diffraction. Full stop. So the sun will look red from Earth. So the sun will look red from Earth. Right, part C. As the sun continues its evolution, its mass will decrease. It is estimated that at its largest radius, the mass of the sun will have decreased significantly. Explain how the orbital period of a planet would change as the mass of the sun decreases. Assume that the radius of the planet's orbit above the sun doesn't change. It's a 3 marker. So guys, starting from F equals ma, if I use it for a planet orbiting the sun, g mm over r square equals m r omega square. So mass of the planet will cancel off. Gm equals r cube. Omega is 2 pi over t square. So if I get the t square subjected, t square equals 4 pi square r cube over g. So now what are they saying? As the sun continues its evolution, its mass will decrease. So the question is, explain how the orbital period of the planet would change as the mass of the sun decreases. So if the mass of the sun is decreasing here, the m is decreasing, orbital period will increase. Correct? So show this working and then make a statement. When the mass of the sun decreases, gravitational attraction will decrease. Gravitational attraction will decrease. So the orbital period will increase. So the orbital period will increase. Okay. Any questions, anyone?
So, that's why the expansion significant.
Yeah.
So, the derivative is that
Based on?
if something is coming close by, the frequency will increase. The derivative will increase.
Mhm.
Same way when the sun is expanding, becomes somewhat
No, that will not be a. It's the sun is not moving away from us. It is in our own galaxy. So if you look at something in a different galaxy, that is a different story. We will speak about it next. Within our own galaxy, you don't consider it. It won't make a. Right. Take a small break. See you in 15 minutes. Okay, guys, in that theory here, turn to page 11. You know this Doppler effect from your O-levels? No? Doppler effect also no? Right. The idea of Doppler effect is this. Simple. Now let's say, guys, remember this example for the Doppler effect. Let's say there is an ambulance. Okay, you're standing on the road. You're standing on the road. And let's say the ambulance is coming towards you with its siren horn. Okay. Now, if it is making a certain sound of certain frequency, let's say it's making a sound of 500 hertz. When it is coming towards you, the frequency that you observe is more than the actual frequency. When it is going away from you, the frequency that you observe is less than the actual frequency. When the source of wave is moving towards you, the frequency that you observe is more than the actual frequency. If the source is moving away from you, the frequency that you observe is less than the actual frequency. This is Doppler effect. Okay? So that is a frequency now I told you. So the wavelength will be other way around. If a source is moving towards you, the frequency that you observe is more than the actual frequency. The wavelength that you observe, is less than the actual wave. Okay? When the wave is moving away from you, when the source of wave is moving away from you, the frequency you observe is less than the actual frequency. Wavelength that you observe is more than the actual wavelength. What do you call this? Doppler effect. It is applicable for any wave. It doesn't have to be sound. It can be sound or light or any wave. The Doppler effect is applicable. So read the note. Page 11. Astronomers first began to look at the spectra of stars in other galaxies during the 1920s. They looked at the other galaxies in the 1920s. They noticed that the spectra looked very similar to the spectra from stars in our own galaxy, but that all the features present were shifted by the same relative amount towards the red end of the spectrum. This phenomenon became known as the redshift. This shift is due to the relative motion of the other galaxies with respect to ours, in an effect called the Doppler effect. An observer receiving waves emitted from a moving body observes that the wavelength of the waves has been altered to a new wavelength. Turn to the next page. A star or galaxy moving away emits light that appears to have a longer wavelength than expected. We also experience this effect when, for example, we hear a car coming towards us and driving past at a steady rate. As it approaches, the note of its engine rises to a maximum pitch, that means a higher frequency, and then falls as the car travels away from us. You could imagine the waves getting squashed closer together as a car drives towards you, and then stretch further apart as it drives away. So, how it is applicable for us in astronomy is, when you look at the light that you are getting to see from another galaxy, that spectrum has a similar spectrum to that is there on the Earth. But the thing is, the wavelength of each light is more than the wavelength of that light on the Earth. Each light, each color has a wavelength more than its color on the Earth. So that means each wavelength is shifting towards the red day. So that is what you call it a what? Redshift. Okay. If you look at a distant star or distant galaxy, the wavelength that you see is more than the actual wavelength. The reason that tells you that galaxy is moving away from us. Okay, this is one of the primary evidences that is available for the conclusion that the universe is expanding. If you see all the other galaxies, they are moving away from each other. So all the galaxies are moving away means the universe is expanding, right? Correct? So this is a clear evidence available to state that the universe is expanding. Universe is getting bigger day by day. Okay. So comparison of light from distant galaxies with light produced on stationary Earth-based experiments can allow calculations of galaxies' speed away from Earth. So using this concept, using the Doppler effect, the speed at which the wavelength is moving away from us can be derived. Okay, so the equation is given here. The amount of redshift a galaxy exhibits allows us to calculate how fast it is moving. This can be done using measurements of either wavelength or frequency changes. So all you need to know is this equation, that is delta lambda over lambda equals delta f over f equals v over c, where lambda is the actual wavelength, delta lambda is the change in wavelength, c is the speed of light, which is 3 × 10⁸ meters per second, v is the speed at which the galaxy is moving away from us. Okay, so let's look at this example. In a laboratory sample, the hydrogen alpha spectral absorption line is at a wavelength of 656.285 nanometers. In a spectrum from a nearby star, this line is observed at a wavelength of 656.315 nanometers. So that means the actual wavelength is this one when you see it on the Earth, but the one which you are receiving from another star has a wavelength of 656.315, which is slightly more than that. Okay. How fast is this star moving and in which direction it is moving? So without any calculation, I can tell you that definitely the star is moving away from us. How do I know that? The observed wavelength is 656.315 and the actual wavelength is 656.285. The observed wavelength is more than the actual wavelength, means that star is moving away from us as per Doppler effect. Correct? To see at what speed we use this equation, delta lambda over lambda equals v over c. So delta lambda is the change in wavelength, which is 656.315 minus 656.285. That is 0.020, let's say, the difference. Okay. That is it. That over the actual wavelength is 656.285. Actual is 656.285. That is equal to v over c, v over 3 × 10⁸. From here you get the v subjected. That is the speed, 13,700 meters per second. That is the speed at which that star is moving away from us. Exactly. Okay. So highlight this equation. This will be useful for you in finding the speed of a star or a galaxy. Okay. Right. Then Page 85, question 40. Oh, wait. Before that. Page 41, question 24. Page 41, question 24. GN11 is one of the most distant observed galaxies in the universe. A redshift Z of 10.96 has been detected by the Hubble Space Telescope for radiation from this galaxy. Radiation with a wavelength of 134 nanometers was emitted from this galaxy. Calculate the wavelength lambda naught of this radiation when it is detected at the HST. Okay. Right. So guys, Z equals delta lambda over lambda. The redshift is equal to delta lambda over lambda. So Z is 10.96. That is equal to delta lambda, change in wavelength, over emitted wavelength is 134. So this tells you how much is the change in wavelength. 134 into 10.96. That is 1468.64 nanometers. Okay, so which means the observed wavelength will be 134 plus 1468.64. Thousand 602 nanometers will be the wavelength that is observed at the Space Telescope. Okay. The next one. Oh, page 77, question 43. The diagram shows the sun rotating about its axis as viewed from the earth. ABC are points on the surface of the sun. Light from points A, B, and C is analyzed. The wavelengths lambda alpha of the alpha line in the hydrogen spectrum is determined for the light from each point. Complete the table with the letters A, B, and C to indicate the point corresponding to each wavelength. Explain why there is a variation in the wavelength of the light from different points of the sun. Guys, now listen to me. Now let's say, now the sun is rotating. Okay, we are here on the earth. We are here, this is the earth. And the sun is here. Okay, it's rotating like this. Okay, now if you take this point on the sun is moving towards us at this moment. Correct? If you take this point is moving away from us. Correct? If you take this point, it's moving this way. It's neither moving towards us nor moving away from us. If you take this point, it's neither moving towards us nor moving away from us. Okay. So now according to Doppler effect, if we get to see a light that is coming from this point, by the time it reaches us, the wavelength that we get to see from this point will be less than the actual wavelength. Am I right? Is less than the actual wavelength. Why? That is coming towards us. This wave is coming towards us. That at that point, the source is moving towards us. So the observed frequency is more, the observed wavelength will be less than the actual wavelength. If you similarly take this point, this one, this point is moving away from us. So that means the observed wavelength will be more than the actual wavelength. Am I right? Whatever the light that we are getting from this point, that observed wavelength that we are getting from this point will be, since it is moving away, more than the actual wavelength. Okay. The light that I am getting from either this point or this point, the Doppler effect is not applicable to those 2 points because it's not moving towards us or away from us. So if you are getting any light from those points, it will be the same as the original wavelength. Agree? Now looking at, that is a theory behind this question. So there are 3 points on the sun, A, B, C. Guys, if you see the point C, it is not moving away from us or towards us. Correct? If you see point B, that's moving away from us. If you see point A, it's moving towards us. Can you see that? B is moving away from us. B is moving away from us. A is moving towards us. The way it is rotating. So now there are 3 wavelengths given. If you see, there is a slight difference in all 3 wavelengths. 656.2837, 2797, and 2757. So the lowest wavelength has to be the point A which is coming towards us, which is the lowest one. 2757, that is point A. The highest wavelength has to be the point B, that is 2837. So then definitely this is point C. Exactly. Explain why there is a variation in wavelength of the light from different points on the sun. Exactly what I told. Write the answer. The point A is moving towards us. The point A is moving towards us. And the point B is moving away from us. Point A is moving towards us, point B is moving away from us. First round. So according to Doppler effect, the wavelengths observed will be different. According to Doppler effect, the wavelengths observed will be different. It's a 2 marker, that's enough. Right, guys, try part C for homework and mark a few more. Page 85, question 48. Question 48. Page 89, question 51. Page 97, question 54. Sorry, page 94, question 54. Question 54. Yeah, that's it for the day, guys. Please read the note that I have sent in the WhatsApp group. Okay, before you come for the next class. Bye. See you. Take care. You're welcome.